primary audio circuit from Reuters Television, Moscow. This is the primary audio circuit from Reuters Television, Moscow. This is the primary audio circuit from Reuters Television, Moscow.
Or not?
Yeah, the Russian broadcast we're getting is quite infrequent. We're not getting a whole lot of information.
Yeah, I think then it may be the same line, and I may end up having to rely on that for whatever information I get.
Okay, well, I'll see. Maybe I can shut off the phone.
Did you just get an announcement now?
What's that?
Did you just get an announcement while you were talking?
I'm not in the room when the announcement is being made. I'm in room 251 and the announcement is the Russian side.
Okay. Okay, if you could check on what's going on there, I'd appreciate it.
Okay, bye.
And, bye. Boris, I'm having a real, are we going to have all this traffic back and forth while we're trying to do this in and out of this door, you know?
Yes, sure. We'll stop it.
Well, if we could, every once in a while, the signal, you know, I don't know whether someone's working with a cable in there, but I've actually lost the picture here a couple of times. It just disappears and comes back.
No, he's trying now, you know, because you see the camera is trembling on
Okay.
the roof
All right.
because of wind. So now trying to arrange, you know, some weight on the tripod to keep it more tight.
Okay. Okay, I will sit here.
Because, you know, this is zoom in and zoom in so that right is up.
Okay.
Then I'll stop right. And there will be no traffic
Okay.
5 minutes prior to your transmission.
Great.
I'll
Thanks.
stop all the traffic here so that these two cameramen, they'll be just standing outside, not blocking your view.
I appreciate that. Thanks.
I know soldiers. Nobody. I know how it's important, you know.
Well, it's a, you know, it's a little, it's difficult not to get scattered in my thinking.
See the wind.
Oh yeah.
Terrible.
The, we have about 9 minutes before we go on the air. I think we're already broadcasting, actually. I just don't know whether they're broadcasting it to the audience in
So we have
Puerto Rico.
9 minutes.
Yeah.
Вот здесь точно абсолютно время. Пуск ровно в 23.
Ага. Ну, у меня похоже. Чуть меня чуть-чуть вперед. Ага. Ветер закричали?
Да. Смягчается. Привяжется.
Не наверху, да? Внизу.
Не надо толкать.
Ну, не понял. Меняется, правильно, меняется.
Там больше никого нет.
Minutes and counting in the latest launch of a Western commercial spacecraft on a Russian-built Proton launch vehicle. Good evening. I'm Eric Larson, and this broadcast is coming to you live from Launch Complex 81 at the Baikonur Cosmodrome in Kazakhstan. This is the 236th launch of the Proton, and it is the second to take place under the banner of International Launch Services. ILS is a joint venture company formed by Lockheed Martin Corporation of the United States, Khrushchev State Research and Production Space Center of Russia, and Russian space complex Energia. The ILS partnership was established for the purpose of marketing commercial launch services on the Proton, and today we will see the continuing fruits of the company's labors with the launch of the Telstar 5 spacecraft. Telstar 5 is built by Space Systems Loral Incorporated of the United States and is owned by Loral Skynet, also of the United States. Our mission this morning is to place the Telstar 5 spacecraft into orbit, where it will join the existing Telstar 4 spacecraft in providing television and data services to the United States. This evening's launch is scheduled to occur at 11 p.m. local time, or 1700 hours Universal Time. The launch window is 10 minutes long. The weather here at the launch site is clear, with some clouds on the horizon. Temperature is 30 centigrade, with winds out of the northeast at 5 to 8 meters per second. Weather conditions currently look good for a launch. During the next half hour, we will be telling you more about the Proton launch vehicle, the Telstar spacecraft, and the mission profile. We will also show you videotaped highlights of some of the previous activities leading up to today's launch. Currently, the Proton launch vehicle, its Block DM upper stage, and the Telstar spacecraft are all progressing nominally through their final launch checkout sequences. This is Proton launch control at T-minus 28 minutes and counting. The launch vehicle for today's mission is the 4-stage version of the Proton, which will be used for the majority of planned commercial launches. It incorporates the large-diameter standard commercial payload fairing, which has been developed by ILS specially for Western satellite customers. The lower 3 stages of the Proton are produced by the Khrunichev State Research and Production Space Center plant in Moscow, as is the payload fairing. The Block DM 4th stage is manufactured by Russian space complex Energia, also in Moscow. Other contributors to the launch today include Saab Ericsson Space of Sweden, who built our separation system, and the Russian Space Forces, whose personnel are performing key tasks in today's launch operations. Overall height of the vehicle is approximately 61 meters, while the diameter of the 2nd and 3rd stages and of the 1st stage core tank is 4.1 meters. Maximum diameter of the 1st stage, including the 6 outboard fuel tanks, is 7.4 meters, or 24.3 feet. The Block DM stage has an external diameter of 3.7 meters. The standard commercial payload fairing is 4.35 meters, or 14 1/4 feet in diameter, and 10 meters, or 33 feet in length. Total weight of the Proton at launch is approximately 691,500 kilograms. The 1st stage of the Proton is powered by 6 RD-253 engines, burning storable propellants and producing a total of 9 meganewtons of thrust at sea level. That's approximately 2 million pounds of thrust when expressed in English units. Proton's 2nd stage also uses storable propellants, which feed 4 gimbaled RD-0210 engines. Total thrust is 2.3 meganewtons. The 2nd stage ignites while still attached to the 1st stage, and the engine exhaust escapes through the open truss structure between the stages until they separate about 4.5 seconds after 2nd stage ignition. The 3rd stage propulsion system consists of a single, fixed RD-0210 and 4 small steering rockets. The main engine develops 600 kilonewtons of thrust and ignites 9 seconds after the steering rockets fire to separate the 3rd stage from the 2nd. By the time of 3rd stage engine cutoff, the payload fairing will have separated, and the Telstar spacecraft, along with the Block DM upper stage, will have been placed into a 200-kilometer circular parking orbit. Approximately 1 hour and 14 minutes after liftoff, the Block DM performs the first of 2 burns needed to place the Telstar 5 into transfer orbit. The Block DM uses an 11D58M engine, which can start as many as 7 times during the flight. This engine burns liquid oxygen and kerosene and develops 86 kilonewtons of vacuum thrust. The overall success rate for the Proton is better than 92.5%, with a success rate for the last 50 flights of 94%. Now we'd like to show you a brief video while we describe ILS in a little more detail. The International Launch Services joint venture of Lockheed Martin Corporation, Khrunichev, and Energia offers the most capable, comprehensive, and cost-effective spacecraft launch services in the world. The constituent companies of ILS have more spacecraft and launch vehicle expertise than any other organizations providing launch services today. Lockheed Martin has built more than half of all Western satellites flown and has designed, built, and launched the Atlas and Titan launch vehicles, as well as the Agena and Centaur upper stages, and the Polaris, Poseidon, and Trident strategic defensive missiles. Khrunichev, in addition to designing and building the Proton, has also produced a variety of missile systems for the Russian government, as well as the Salyut, Mir, and Almaz orbital stations, and several different orbital return capsule designs. Energia has provided all of the 4 stages for the Proton since the program began. They are also the designer and builder of the R7 series of space launch vehicles, including the Soyuz and Molniya launchers, of which more than 1,300 have been launched to date. During the 1980s, they designed both the Energia Heavy Lift launch vehicle and the Buran space shuttle, in addition to significant portions of the Mir space station. ILS has access to all of the resources of its constituent companies and provides a management approach that has been developed to ensure efficient task completion with essential focus on customer satisfaction. This is Proton Launch Control at T-minus 23 minutes and counting in the launch of the Telstar 5 mission. The Proton has a long and distinguished history with a record that includes a number of significant firsts. It has also become one of the principal workhorse vehicles of the Russian space program. Development of the Proton launch vehicle began in the early 1960s under the direction of the Soviet academician V.N. Chelomey. The first launch took place in July 1965. This was a two-stage version of the vehicle that was used for a series of 4 test flights. That first version of the Proton has since been superseded by 3-stage and 4-stage models, both of which are currently in use. An improved version of the Proton M, is now in development. The Block DM fourth stage was developed independently during the 1960s as the 5th stage of the Russian manned lunar launch vehicle, the N1L3. It was originally known in Russia as the Block D, where block is the common translation of the Russian word denoting a rocket stage, and D is the 5th letter of the Russian alphabet. The vehicle was upgraded during the 1970s to the current Block DM, or modernized version. Proton has flown well over 200 missions and has orbited the Salyut series space stations and the Mir space station modules. As a 3-stage vehicle, the Proton has become Russia's principal heavy-lift launcher. The 4-stage Proton has launched the Ikran, Raduga, and Gorizont series of geostationary communication satellites, as well as the Zond, Luna, Venera, Mars, Vega, and Phobos interplanetary exploration spacecraft. These missions produced the first samples of the lunar surface to be returned by an unmanned spacecraft and the first soft landing on the surface of Venus. All Russian geostationary and interplanetary missions are launched on Proton. Approximately 90% of all Proton launches have been of the 4-stage version. The future promises to be very busy for the Proton. Western satellite builders and operators have already signed numerous launch service contracts for Proton, with the potential to produce up to 8 commercial launches per year through the end of the century, in addition to the 4 to 6 flights that will be conducted annually for the Russian government. The upcoming International Space Station will also rely on Proton to launch its first component, the FGB bus, as well as the subsequent service module. This is Proton Launch Control at T-minus 21 minutes and counting. Propellant loading of the Proton began this afternoon at T-minus 8 hours when the command was given to evacuate the last of the spacecraft and launch vehicle support personnel from the area of the launch pad. Actual propellant transfer operations began at T-minus 6 hours when the nitrogen tetroxide oxidizer, an unsymmetrical dimethylhydrazine fuel that powered the first 3 stages of the Proton, started to flow into the vehicle from ground storage tanks through a set of fueling connectors at the base of the vehicle. The Block DM upper stage was filled with kerosene before the Proton arrived at the launch pad. Liquid oxygen loading of the upper stage began simultaneously with the start of propellant transfer to the first 3 stages. The liquid oxygen is loaded through a connection from the mobile service tower. The nitrogen tetroxide and UDMH used in the first 3 stages, as well as the kerosene used in the Block DM, are all liquids at room temperature and require no special thermal conditioning. Liquid oxygen, or LOX, is a cryogenic propellant that must be maintained at minus 290 degrees Fahrenheit. The LOX tank of the Block DM, however, is heavily insulated, and so very little boil-off of the propellant occurs between the time the LOX is loaded and the moment of liftoff. Propellant loading of the Proton launch vehicle in the Block DM upper stage was completed at T-minus 2 hours and 55 minutes. This is Proton Launch Control at T-minus 19 minutes and counting. The Telstar 5 satellite, manufactured by Space Systems Loral Incorporated, is an FS-1300 3-axis stabilized model. It is roughly cubical in shape and composed of various modules. The primary structure, called the bus, contains the spacecraft's propulsion system, electronics, and battery packs. The payload is that portion of the satellite that makes up the actual communications equipment and solar panels. Telstar 5's communication payload consists of 24 C-band and 28 Ku-band transponders. Telstar 5 weighs 3,650 kilograms at launch. The solar arrays measure more than 31 meters across, and the antenna is more than 8.6 meters when fully deployed. Telstar will be launched in a stowed configuration and deploy its communications reflectors, telemetry and command antenna, and solar panels following separation from the launch vehicle. Once on orbit, Telstar 5 will uplink television and data channels from various sites in the United States and then downlink these signals to ground stations throughout the U.S. It will also provide direct broadcast television services. We now have a short video describing the processing of the Telstar spacecraft in further detail. Here we see preparations underway to encapsulate the spacecraft returning from the fueling hull prior to its attachment to the rest of the Proton launch vehicle. The spacecraft here is being lifted and will be transferred over to mate atop the Saab-provided adapter. Here we see the spacecraft being lowered onto the adapter. The final alignment of the spacecraft prior to mating with the adapter. And the final adjustments of the positioning of the spacecraft on the separation system before the attachment of the clamp band. Here we see the finished clamp band assembly in place, ready for flight. This is the hardware that will separate the spacecraft from the Block DM upper stage at the completion of this evening's launch. Now we see the combined spacecraft and adapter being prepared for mate to the fourth stage of the Proton. In the background, you can see the Block DM in its integration and rotation fixture. Here we see the spacecraft and adapter combination carefully being lowered into place atop the Block DM fourth stage prior to the stage's rotation and the spacecraft's encapsulation. Now we see the payload fairing being mounted around the spacecraft. And the two halves of the payload fairing being mated. Following the mating of the two halves of the payload fairing, closeout operations are begun. and the completed payload fairing spacecraft and upper stage assembly, called the Space Head Unit, is lifted onto its transportation car and moved over to the Launch Vehicle Integration Building to be mated to the first 3 stages of the Proton. This is Proton launch control at T-minus 12 minutes and counting. The launch window for this morning's mission is 10 minutes long, which is considerably shorter than the 1 hour or so that would usually be encountered when launching spacecraft such as Telstar on another launcher. The reason for this is the fact that the Proton does not perform right ascension of ascending node steering, so the time of launch is rigidly determined by the allowable errors in the accuracy of orbit insertion. Even so, most Proton launch delays have been the result of payload problems. The Proton itself has rarely missed a launch window. If for some reason the launch cannot be accomplished this evening, another 10-minute window will open at 11 p.m. again tomorrow. On the right side of the image in front of you is the Proton's mobile service tower. It's now standing 200 meters away from the Proton in its final position prior to launch. Rollback of the MST began at T-minus 1 hour and 10 minutes and was completed approximately 1/2 hour later. The MST stands more than 70 meters tall and provides a variety of services to the Proton. You will remember that liquid oxygen for the Block DM upper stage is loaded from the MST. Also, the service tower provides a temperature-regulated airflow to the Proton's payload fairing in order to maintain the Telstar spacecraft's temperature within acceptable limits while the Proton sits on the pad before launch. Airflow to the spacecraft from the MST was disconnected 15 minutes prior to rollback. Thermal regulation of the Telstar 5 is now being provided by a set of radiators mounted inside the payload fairing, which circulate a cooling fluid. This liquid-based system will be disconnected and purged by dry nitrogen gas at T-minus 5 minutes. The mobile service tower also protects the Proton from high winds, although in reality, winds are rarely an issue during a Proton launch. Even with the large diameter payload fairing we're using today, the Proton can lift off in winds as high as 16.5 meters per second. That's about 38 miles per hour. The MST doesn't have to be brought back to protect the Proton until ground wind velocity exceeds 20 meters per second, or more than 45 miles per hour. We have some footage of the mobile service tower and of the Proton's rollout to the pad, which we would like to show you now. Here we see the completed Proton launch vehicle being lifted off of its assembly fixture and onto its transporter erector car for transportation out to the launch pad. Here's the open door of the Launch Vehicle Integration Building as the Proton begins its rollout. The distance from the Launch Vehicle Integration Building to the pad is about 4 kilometers, and the overall travel time is approximately 2 hours. Here we see the Proton erect on the launch pad. Operations to connect the Proton to the pad were completed shortly before dusk on Tuesday evening. During tonight's launch, the first 3 stages of the Proton will follow a standard ascent trajectory to place the 4th stage and the Telstar 5 spacecraft into a 200-kilometer circular parking orbit inclined at 51.6 degrees to the equator. Once in parking orbit, Telstar will be propelled to its transfer orbit by the Block DM upper stage. The targeted parameters of the transfer orbit include a perigee altitude of 6,700 kilometers, an apogee altitude of 35,786 kilometers, and an inclination of 17.5 degrees. Once in transfer orbit, the Telstar 5 spacecraft will separate from the Block DM at a mission elapsed time of 6 hours, 41 minutes, and 51 seconds. Telstar will then deploy its solar arrays and conduct checkout operations for several days before igniting its own onboard liquid apogee engine 3 times over a period of 4 days to place the satellite into its final geosynchronous orbit. Deployment of the reflectors will take place on May 31st. Just a few minutes ago, the Telstar 5 spacecraft manager signaled Telstar's readiness for launch. At T-minus 5 minutes, the Proton's first 3 stages will confirm they're okay to launch, and at T-minus 1 minute and 53 seconds, the Block DM upper stage will give the final go for launch. The engine start command will be given by the automatic sequencer at T-minus 2.5 seconds. Let's listen for announcements from the firing room as we enter the final moments before launch. This is Proton launch control at T-minus 5 minutes and counting. The firing room has announced a last synchronization of the onboard clocks. All of the Proton stages and the spacecraft have checked in and reported readiness for launch. All of the stations in the firing room have reported in and confirmed their readiness for launch. T-minus 2 minutes to launch. We're coming up on the T-minus 1 minute mark. Mark, T-minus 1 minute and counting. T-minus 30 seconds. T-minus 15 seconds. 10, 5, liftoff. We have liftoff of the 236 Proton carrying the Telstar 5 spacecraft on its way to geosynchronous orbit. We're 100 seconds into the flight and everything still looks good. In 120 seconds, we should be coming up on stage 2 ignition. There we have it, stage 2 ignition. Stages have separated properly. Everything is still go. In 60 seconds in flight, everything is still good. 200 seconds into the flight, well into the burn of the stage 2 and the flight of Proton with Telstar 5. Still looks good. The flight is still nominal.
250.
At 335 seconds, we'll be coming up on stage 2 shutdown and stage 3 ignition. – 300 seconds and everything is go. The 30 coming up on stage 2 shutdown, stage 3 ignition. – 360 seconds into the flight, everything still looks good. Launch control is still reporting that all parameters look good. Main engine burn is still going well on the 3rd stage. By now, the payload fairing has separated.
5, 5, 10.
By now, the stage 3 main engine has shut down.
Shut down. Final moment. Third stage burn. Separation of third stage.
And that was confirmation that the 4th stage has just separated from the 3rd stage. The Block DM and the Telstar 5 spacecraft are now in a 200-kilometer circular parking orbit. Everything still seems to be going well. Ladies and gentlemen, we're going to be ending our broadcast in a few minutes, but before we do, I want to describe for you some of the upcoming events in this mission. About an hour from now, the small rocket motors of the Block DM's attitude control system will begin a 5-minute burn to settle the propellants in the stage's tanks. At the end of the settling burn, the main engine will ignite and then operate for 393 seconds in the first of 2 firings of that engine that will occur during this mission. 5 hours and 6 minutes later, the main engine will ignite again, this time for 110 seconds, in order to complete the task of placing the Telstar 5 spacecraft into its target geosynchronous transfer orbit. Spacecraft separation and the completion of the Proton's commercial mission will occur 20 minutes later at L plus 6 hours, 41 minutes, and 51 seconds. A lot of people were responsible for making the launch we've seen this evening and the subsequent orbital operations as successful as they have been so far. I would like to take the time to congratulate the members of the ILS launch team here at Baikonur for their expertise and dedication. I would particularly like to congratulate the members of the Russian Space Forces and the employees of Khrushchev Center, RSC Energia, Lockheed Martin Corporation, Space Systems Loral, and Saab Ericsson for their hard work and cooperation in carrying out this mission. Finally, I would like to thank Loral Space and Communications Limited for their vision in selecting the Proton to launch Telstar 5. This launch represents the continuation of a long and productive relationship between Loral and International Launch Services. Again, this is Eric Larson from the Baikonur Cosmodrome in Kazakhstan. This concludes our launch broadcast. Have a good evening.
This is the primary audio circuit from Reuters Television, Moscow. This is the primary audio circuit from Reuters Television, Moscow.